Okay, so the last thing we're going to take a look at in this section is interpreting what are known as phase diagrams, right? So these are going to be different than the heating curves or the cooling curves that we saw previously. What phase diagrams are things that summarize the conditions, and the conditions that we're going to be looking at here are temperature and pressure conditions. Whereby a substance can exist as a solid or a liquid or a gas. Right, and we'll identify three general regions in every phase diagram, and this one here is a good depiction of what phase diagrams typically look like. On the y-axis, we have the pressure level. Well, that's usually in atmospheres. And then on the y-axis, the x-axis, we have temperature, usually in degrees Celsius, but it can really be any temperature needed. We have our three different regions. The leftmost region is going to be the solid region. The rightmost region to the right side of the graph is the vapor or the gas region. And then in between both of those will be the liquid region. Right? And each of these three regions is separated with a line. And what that line is it represents the red lines in this particular example. Represent the phase boundary between each of the physical states that it borders, and that tells us the conditions under which those physical states can exist together, can exist in equilibrium. The physical states. Can exist together, equilibrium with one another. So, for example, in this diagram that we have here, if we look at, you pick any point along the red line, you pick this one here, for instance, in green, this point here. This is the point at which the solid and the liquid can both exist in equilibrium with each other. So whatever this pressure is, we call that P, and then whatever this temperature is, we call that T. Right, that's the pressure and the corresponding temperature at which the solid and the liquid can exist together. So in other words, going from the solid to the liquid, that's the melting point, and that will be the melting point at that particular temperature. This is a temperature corresponding. Each of the lines, they do intersect at one region that's known as the triple point. So in this case, that's this region here. And what the triple point is, just like with the other lines that we've seen before, this is where all three of the phases, solids, liquids, and gases, exist in combination or exist together in equilibrium. So there's a particular pressure and temperature associated with that triple point as well. Now, what you may notice also in your phase diagrams, in every single one of them, is that there is going to be a region and that region, that part on the phase diagram is this region here. And that's what the distinction between the line between the liquid and the vapor, where it just seems to end. And that's this region right here. And we refer to that as the critical point. And at that critical point, we have two important pressure and temperature. So at that point, we have what's known as the critical pressure, so P subscript C. And at that point, we also have the critical temperature, we call it P subscript C. So the critical temperature for that substance, which you see is the temperature above which, above that temperature, you cannot liquefy that gas. The temperature above which the gas cannot be liquefied. No matter how you change the pressure. So regardless of the pressure, right? So if we increase the temperature, for example, from this point onwards, there is no way to get it back into the liquid phase or the liquid state. The critical pressure is the pressure needed to liquefy vapor at the critical, the minimum pressure needed to liquefy a substance. At the critical temperature. So the reason why this is important is because temperatures above the critical temperature, okay, so above the critical temperature in this region over here, there really isn't any distinction between the liquid and the gas. All we have is just a fluid, and a fluid that is at a temperature and pressure that is above the critical temperature, above the critical pressure. We refer to that as a supercritical fluid. And these are not very common, but in some cases they are very useful. They have very distinctive properties. And in some cases they're used as solvents in several industrial applications. And one example of that was the use of supercritical carbon dioxide in the decaffeination of coffee, right? How do you get the caffeine out? Well, the supercritical CO2 can be used in that process. So the phase diagram we've been looking at so far, this is actually the phase diagram for carbon dioxide. And it's fairly typical in terms of how phase diagrams look. This is for CO2. And then what we can do here is actually see how the different phases change as we adjust or alter the temperature or the pressure for different substances. So we can see there is no liquid phase above, for instance, I'm sorry, there's no liquid phase below 5.2 atmospheres for CO2. So if we have a carbon dioxide, for example, that is, let's say, at normal atmospheres, so about 1 atmosphere of normal conditions. Let's say it's at negative 100 degrees Celsius, maybe like right about here. And then we increase the temperature, so we warm it up, let's say, for example, to room temperature, which is, let's say, about 20 degrees Celsius over here. So as we go at 1 atmosphere, so the pressure doesn't change, it's at sitting up on your table, for example, at home, right? This is solid CO2 at this point. It's in the purple region, solid carbon dioxide. And I just increase the temperature of it, but I'm going to go all the way across here till I get to the temperature, room temperature, let's say this. So what's happening in terms of the phase changes with solid CO2? It goes from the solid 1 atmosphere, if we increase the temperature, what happens is it goes from the solid, it doesn't go to the liquid state because there is no liquid state for CO2 under 5.2 atmospheres, and at normal conditions, we're at 1 atmosphere. So it goes from the solid directly into the vapor, right? And that process is sublimation. So under normal conditions, then solid carbon dioxide, which is commonly known as dry ice, goes from the solid to the gas phase. So the vapor phase, there is no liquid phase altogether, so it just goes into the air and it wafts around and it's gone. Right? It doesn't melt into a liquid, which is one of the reasons why it's called dry ice, right? As opposed to regular ice that actually does melt under normal conditions into a liquid. So we started at let's say where were we, like at negative, let's see, 100 degrees Celsius for CO2. We increased the temperature. We got eventually to this temperature here, negative 78, which is the point at which the CO2 goes from the solid to the gas phase. So that's the sublimation point there of CO2. And then once it turns into the gas phase, well, then we heat it up, the temperature of the gas increases till we get to the room temperature. If at this point we were to increase the pressure, we can actually now, if we increase the pressure, we can eventually get to this point to maybe, maybe 10, 12 atmospheres. We can force the CO2 gas to actually liquefy. So we can increase the pressure. That we call the CO2. Okay, so we can, if we know where we're starting off on our phase diagram, we can chart, we can take a look and see how the phases change as a function of changing the temperature at a constant pressure, or changing the pressure at a constant temperature as well. So this phase diagram is going to look very similar to most of the other substances. We can compare that then to the phase diagram for water, and this is the one that we have down here. This is for H2O. And what we will see, especially when you compare it to most of the others, is that it looks similar. We have the solid on the left, the vapor over to the right side, the liquid in the middle. But the main difference here is the fact that the solid liquid line, so this line here for water, actually there's a negative slope to it. Whereas in the case of CO2, it's actually a positive slope. In the case of water, that negative slope is very unusual. That's not normal. It's unusual. And it has some implications for how water is going to behave under these different conditions. So a couple things to note here. The triple point for water is you have the pressure that corresponds to 0.006 atmosphere. That's a very low pressure. And then we have a temperature of just above 0 degrees Celsius. That's 0.01 degrees Celsius. Right? This here is a triple point. Temperature and pressure at which all three physical states exist. Equilibrium. That's a very, very low pressure. A pressure of 1 atmosphere, this is under normal conditions. So if I were to draw a line at 1 atmosphere of pressure all the way across, I can see where the temperature at which we go from the solid to the liquid phase, that would be the normal melting point of going from the solid to the liquid. So that's no melting point of ice, or the normal freezing point of water if you're going in the other direction. And if you continue this all the way across, now the liquid temperature increases, we get to the temperature at under 1 atm at which the liquid turns into the vapor. So then at this point, that would be the normal boiling point. of liquid water, and then that corresponds to 100 degrees Celsius, and then the melting point corresponds to 0. Right, so this is key here. When we look at the temperatures for the phase changes at 1 atmospheric pressure, those are referred to as the normal melting point and boiling point, respectively. Right, in the case of carbon dioxide above, there is no melting point, there's no boiling point at 1 atm because we go directly from the solid to the gas phase or the vapor phase. So it's the sublimation point. So the fact that the solid liquid slope here slopes backwards, in other words, or there's a negative slope, has implications like we mentioned. And one of those happens, for instance, if you were to go, let's say, ice skating, for instance. So let's say you go on to an ice rink or something, and we have ice obviously on there. The pressure that the ice is being exposed to is about 1 atmosphere. Now let's say the temperature of the ice may be a little bit less than 0 degrees Celsius, maybe about 1 or 2. So that's what we're starting off here. 2 degrees Celsius. So that's where we're at. So when you start and go on the ice with some ice skates and you step on the ice, what you're doing is you're actually now increasing the pressure, right? So the temperature is still whatever the temperature of the ice is, -2 degrees Celsius. But as you increase the pressure now, we can draw a line. So pressure is going up this way. And what you'll see is that we go from the solid now into, let's say, the liquid state, so the liquid state at the same temperature, because all we're doing, right, the temperature is not changing. We're just with the ice skate on there, you're standing on this really, really thin blade of ice, and that's exerting a really high pressure in that little region that you're standing on, and it causes the ice to melt. It goes from the solid to the liquid phase, and that's how you're able to slide. And as soon as you move off from that region on the ice, well, then the pressure falls back down, and guess what? You go back to the solid phase. So it refreezes behind you as you move away from that region on the ice. So something as simple as using ice skates on a sheet of ice actually has or can be explained by this negative slope of H2O. The fact that it slopes backwards, in other words, means that if you increase the temperature, increase the pressure at a constant temperature, causes the solid here to melt into the liquid. And then similarly, if you were to lower the pressure at the same temperature, you would find that the liquid turned back into the solid. Right, and that's very different than what you would notice in other cases where there's that positive slope increasing the pressure at the same temperature tends to turn something into a solid rather than a liquid, and that's not the case for H2O. All right, so let's take a look at another example of interpreting these phase diagrams. So we're provided one here, and it says determine the normal boiling point and the normal melting point of the substance, and then determine the physical state that would be present at a pressure of 2 atmospheres and a temperature of 110 degrees Celsius. Determine the pressure and temperature that correspond to the trigger point. All right, so let's see, the normal boiling point and melting point correspond to the temperatures at which we go from the liquid to the gas phase and the solid to the liquid phase at 1 atmosphere. So we want to then identify the 1 atmosphere. We can draw a horizontal line all the way across our phase diagram until we encounter these phase boundaries. And then we also then need to know what these different regions represent, right? So we said generally on the left side of the phase diagram, we're going to have our solids. On the right side, we're going to have our gases or vapor. And then in between, we're going to have our liquids. All right, so at 1 atmosphere, going from the solid to the liquid, is this region right here, or that point right there, that corresponds to the melting point at 1 atm. That's the normal melting point. And if we were to draw a line down vertically, you'll see that's about, well, should be about 140 degrees or so Celsius. And that's the melting point. But follow that further down the line at 1 atm, where we go from the liquid to the gas phase right about here. That would be the normal boiling point, and that would correspond to just over 200. So maybe about 205 or 210 degrees Celsius. That's the boiling point, right? And again, those are under conditions of 1 atmosphere pressure. Part B, it says determine the physical state of the substance at 2 atms. So that's 2 atms here. Draw a horizontal line, and 110 degrees Celsius. 110 would be maybe about here. So we just see where these line up, where they intersect right here. And that is smack dab in the middle of the solid phase. So when you're under the conditions, it's going to be solid. And then part C, determine the pressure and temperature that correspond to the triple point. So the triple point where all three lines intersect, that is going to be right here. And that seems to correspond to about 110, just a little bit above. And then the pressure here is about 0.7 or 0.8. Right, so we can interpret our phase diagrams, first of all, knowing the regions, solids, liquids, and gas regions, and then the lines that differentiate one region from the other. Any point along those lines would correspond to a phase change, conditions for that. Going from the solid to the liquid, or the liquid to the gas, or in other cases, going from the solid to the gas, which is a sublimation.